this webinar that we are hosting. It gives me great pleasure today, October the 6th, 2022, to welcome you all to the Fall 2022 seminar series put together by the graduate student community of the Gallipoli College of Engineering. A little bit about the GSC leadership. Roshan Samir is a co-chair together with Rachel Bennett. For publicity, we have Andrew and Avinash, and the support team is growing. And we have Anirban, who represents us on the Graduate Student Senate, Swapnil Dhyanat, who is co-chair of the social activities that we have. Mayank Filani Lance is also the co-chair of the social events. Nurian Tia Mew has joined us recently, and so has Suraj Patel. And I'm the faculty mentor for the GSC. We have regular meetings. The graduate student leadership team meets every Wednesday, and everybody is welcome. We do it by Zoom, so please contact Rachel Bennett or Roshan, and we meet on Wednesdays at 5 p.m. To become a GSC member, just scan the code, and so I'm going to give you a few seconds to scan the code so that you can join the GSC. And this really helps the GSC because we get funds from the GSC, from the Graduate Student Senate, and the more members we have, the easier it becomes for us to get funds. The GSC maintains a Facebook page. The GSC has a YouTube channel. So all the videos that we put together, all the webinars that we host get put up onto this YouTube channel. And it is a very good source for people to see what webinars we've had, and the content is quite exciting. We also have a Dave and Susan Burt team room for all GSC members. And if you're interested, please get in touch with Roshan or with Rachel. And in this room, it's well equipped. There's a microwave oven, there's a coffee maker, and there's the internet, and you can sit and you can talk and you can make things happen. And the entrance is by electronic card. We pretty soon somebody will be putting up in the chat a attendance sheet. Do fill that attendance sheet up, because this allows us to get funding from the Graduate Student Senate. And now I invite Janet to introduce Jacob. And
so it is really a pleasure to have Jacob talk today. He has worked with Farouk and me while he was an undergraduate here for about 2.5 years. And this is one of the things he has accomplished. It's a remarkable piece of work. It helps you formulate a problem when you have many, many different possible directions to go. So he's going to talk today about market structures for a low carbon hydrogen economy. Jacob?
Jacob has been co-mentored by Chandra Rai and Deepak Devakanta. Go ahead, Jacob.
Okay, so yes, as they have said, okay, I can't screen share. There it is. Okay, so why isn't it? Thought I muted that. Not using time. Here, my bad. Okay, so as Dr. Allen introduced me, my name is Jacob Starks. I am currently in my master's on post-tension slab foundations with expansive cements. That is not what this project is actually on. As an undergraduate, I worked with Dr. Allen, Mistry, Dr. Rai, and then Dr. Dev Gowda, also from the Petroleum Engineering Department, was involved in this project of evaluating the state of the industry in Oklahoma for a hydrogen economy. In particular was the emphasis in the state, but at a wider scope, the idea is also for this to expand to a hydrogen economy in general. And this was presented at IDTC this past August with the paper titled number 9367, Framing an Evolving Market Structure Using a Business Model Canvas. So, quick overview. In general, we're currently facing an economy and society in general where we have significant complex challenges: climate change, rapid transitions to automating a lot of industries and jobs that, again, normally were done by hand, incorporating a lot of smarter systems for, self-driving cars, for management of energy systems, healthcare. So this, combined with technological progress to actually enable all of that, have led to rapidly developing and evolving markets, where we face this issue of we're trying to bring in these new technologies and we need to assess how they're going to impact the economy and society to present this as a feasible business plan and address the needs both from a supply side and from a consumer perspective of how this is going to be viably implemented in practice. And this requires more than just saying, okay, how are we going to assess the technical needs for these challenges we're trying to address, these problems we're trying to solve, or how do we solely make this economically feasible? This requires a far more holistic assessment of how is bringing these new technologies to market going to affect other related industries. So one very good example of this is the automotive industry, where you have electric cars coming to market, and that's now affecting not just bringing cars to market and how does that affect what's on the road currently. How do we adjust our infrastructure so that it can now handle the fact that you need, refueling stations for these cars so that people can drive them? How do you factor in that's now going to put a significantly higher demand for electricity on the grid? You have all these kinds of indirect impacts, both in some regards positive, some regards negative, that need to be assessed beyond solely considering how do we simply technically make a new technology and bring it to a market at a certain price point. Further complicating this is the fact that when we're discussing this idea of an evolving market, most of the time, these technologies that are being presented aren't at the point of maturity. They're still immature, still developing as people are trying to realize them and bring them to industry. So in the case of going back to our fun example of electric cars, you have many of these cars were still being developed as they were coming to market, with the capacity of their battery storage being improved, being made safer so that they could be facilitated in industry. But at the same time, while that is viable, you still need to be assessing business needs for implementation. A major issue is that a lot of times people consider this as an issue of, we'll make it completely functional, we'll reach this point of maturity, and then we'll assess, what we need in the market to bring these products to a viable state for people to start adopting. But that's too late. For these electric vehicles, we take that example again, just because it's such a nice picture, is that you had people bringing cars to market, but then for years, even with government subsidies, you had a very small fraction of people willing to and able to adopt this because there wasn't infrastructure in place for being able to refuel outside of your house. So you in order for you to be willing to adopt it and able to actually use it viably, you had to be willing to install in your own house the ability to charge. And you had to have a limitation that you were okay having a vehicle that can only travel so far away from your house. So if you needed to take long trips cross country or between states that exceeded, say, the 200-mile charging capacity of your car, it simply was not viable for you to adopt, even if you wanted to, which again brings up the other aspect of that, in that you have this distinction between viability and feasibility. You can bring a product to market and people can use it, but that does not mean people will use it. There have to be incentives in place to encourage users to not only have access to a technology, but want to adopt and utilize it. A significant situation where this is a case is in the case of the hydrogen economy, which has been pitched as this revolutionary way to really combat climate change, revitalize the energy industry, and address many of the gaps in the market. And that is very feasible if it's done right. Hydrogen, even compared to other technologies such as solar cells, a lot of these battery technologies for electrification of the grid and energy usage, wind turbines, nuclear, all of these technologies are far further along in terms of development versus hydrogen. And as a result, hydrogen, if you really start looking at it, is falling into a lot of the pitfalls that faced many of these technologies as they developed, where at its immature stage, the important focus as far as most in research emphasis and business interest is on solely how do we do this economically? How do we produce it economically? And we'll, worry about other problems that are going to come with implementation later, ignoring any sort of supporting infrastructure that's going to be required. And the point here is that assessing that business need for implementation at that point, once it's already reached that maturity, is going to be too late. We've seen that time and time again with a lot of these renewable technologies coming to market, that it's taking years, if not decades, for them to finally get adopted if that gets ignored, if at all ever being used. For evolving markets, there really need to be policy efforts to balance your technical, economic considerations upfront to reach maturity, as well as the management and system level analysis required to holistically assess how do we not only make it a functioning technology, but make it a technology that's viable for people to actually use. And in this project, we've utilized the business canvas model to really assess current technical and gaps in industry, as well as economic shortfalls, as well as looking at research for what gaps there are from a management and implementation perspective to address future challenges and bottlenecks that we're potentially looking at if we wait to that point of maturity before we start addressing implementation concerns. So what we can really see here from this survey was that while Oklahoma is honestly one of the most ideally placed locations to address the limitations of hydrogen in its immature state, current policy goals are really overlooking a lot of the implementation needs, which will inevitably cause bottlenecks in actual implementation. Firstly, hydrogen infrastructure for distribution and storage are really critical assets for progress. Hydrogen has three real value propositions that it provides beyond just using renewables or fossil fuels that are currently on the grid. And that's one, that it's a scalable technology in that you can have fuel cells that you can employ at as small a scale or as large a scale as you really need for usage, depending on the market sector that you're in and regional needs. Secondly, you really have this goal of it has this interplay and interoperability between existing fossil fuel resources and the less developed resources of renewables, because renewables really have this gap in that their variable production They are regionally disparate in where you can actually employ different renewables. You can't use hydropower unless you're near the ocean or another large body of water that has enough tidal behavior or flowing water that you can actually employ turbines without causing significant disruption. You can't use solar cells unless you're in a region that gets enough sunlight for that to viably produce enough energy to make back any losses that are incurred. You can't use wind turbines if you're in a really tight packed city. So you have all of these limitations in terms of not only where you can place renewables, but when and how much they're going to produce that really limit how useful they are without a storage capability at scale. On the other hand, you have fossil fuels, which fundamentally, even if we don't face this risk of climate change, are a finite resource that will run out in a couple decades. So they're not a long-term sustainable resource. But with hydrogen, you have this interplay where you can utilize it to both leverage the storability and versatility that you get with fossil fuels, but shift to a more sustainable and viable resource with your renewables. And because hydrogen fundamentally can be produced or converted from either source. Finally, you have the storability being the major component in that it really helps to help regulate the grid. However, all of that benefit doesn't fundamentally come from the economical production that people are focusing on currently. It comes from all the supporting infrastructure behind it. The pipelines that allow you to move resources from an area where renewables might be highly produced to somewhere where they can't be. The storage capabilities to store renewables when they're in a moment of peak production and keep that for when it reaches peak demand. The business canvas shows that we've really overlooked a lot of those considerations by solely focusing on production. And additionally, we've overlooked the need for management to regulate the whole supply chain so that that can truly be effectively and efficiently allocated and realized. So as I've mentioned, we use this business canvas because it really works well for reframing a technical problem in terms of the surrounding business environment in which you're trying to solve that problem. It divides basically the market up into 9 key sectors, starting centrally with this value proposition. And then on the right-hand side, you have all your demand needs. On the left-hand side, you end up getting all of your supply side needs, which then allows you in the end to address it not only from a technical perspective in the upper half, but down below in terms of how this actually translates to a truly viable business plan through pricing, business valuation, and how you're going to structure the financials that the technical side supports. This really allows for reformulating, especially a problem like this that is immature, into what currently exists out there, what is currently developing that will help or hinder this goal that we are trying to solve, and then finally, how will what we're doing affect this market that we're currently viewing, which allows you to truly iterate through what your global solution in an industry setting is. Why are we missing? We're missing some slides. I apologize. I don't know why these are hidden. These were there. My bad. Sorry, guys. Oh, these are. Okay, there we go. So to establish this business canvas, we used over 80 research papers covering all aspects of the hydrogen supply chain, half a dozen industry reports, including these 3 in particular from the DOE, IEA, and then McKinsey & Company. And then we also looked at industry reports from specific companies such as ConocoPhillips, Williams, and the interests and initiatives they're looking for in hydrogen to truly try to create a holistic assessment of everything that's going on in the market and in the industry, looking at the hydrogen space, where they're interested, as well as where they're trying to develop. And what made this extremely useful is that we actually had the state of Oklahoma, with a joint effort from some of the leading members here at OU and at Oklahoma State, create a state report through their Oklahoma Hydrogen Task Force as to a more conventional analysis of where the hydrogen market is and where it's going, which really creates a contrast that allows us to see how this method here contrasts with a more conventional analysis and potential gaps that are formed there. So based on all of those sources, we were really able to compile our business canvas here to assess all the needs and gaps that we can see. And really where we see there are fundamental gaps are in how we're going to address the storage concerns that really allow for our value propositions in bringing a storable, resilient energy grid to fruition is fundamentally overlooked. For example, just in 2021, over $130 million were dedicated by the DOE to specifically hydrogen production initiatives in research. Contrasting that with the fact that in the past decade, only $4 million have been dedicated specifically to research initiatives focusing on storage, which fundamentally shows that there's a gap in where people are considering the true value from hydrogen to come from. Hydrogen production, even if it becomes extremely economical, even if we can reach this point where you can use hydrogen as cheaply as you can use gasoline, if you're missing the storage component that allows you to regulate supply production, which is highly variable with when peaking demand occurs, then using a resource that's less valuable than anything on the grid, because hydrogen doesn't in of itself constitute an energy resource. It's derived from a conversion of fossil fuels or wind power or solar into hydrogen for usage in fuel cells. So there are inherently in that process, you're going to incur efficiency losses. So you're wasting energy, even if hydrogen becomes cheap enough to use, and you're not gaining any of the resiliency propositions that hydrogen supposedly is here to provide to the grid. Additionally, there's this major gap that's missing in terms of management considerations, in that even if we bring hydrogen to market, now we have one more resource on the grid that we need to decide how we're going to regulate this and decide when are we going to tap into reserves of hydrogen that we've produced to supplement the grid? When are we going to produce reserves of hydrogen? Or when are we going to overproduce wind, solar, so that we can make hydrogen reserves that could then be used at a later time? That is a massive system-wide regulation and management problem that is completely unaddressed by almost all the funding proposals. There's been $14 million dedicated to that in 2021, which again is 8% of the massive $130 million of funding proposals that the DOE has awarded in 2021 alone. Of course, it's one thing to say all this purely through, abstract, looking at just financial data and text and what people are putting out in reports qualitatively. But let's do a quick quantitative example by doing a quick forecast of the system demand. So in the first 2 quarters of 2021, we can see, based on data collection from Mesonet and the Southern Power Pool, the approximate wind production and electricity demand in blue for the state of Oklahoma over those 6 months. As you can see, we're producing a very significant fraction of our energy. In fact, on average, we're producing almost 35% of the state's electricity demand is produced through wind power. However, there's a major problem in that we're actually only utilizing about 37% of that, because that's almost 20% of the wind power, because of gaps between when electricity is being demanded and when it is being produced, that has to be redistributed elsewhere across the region, or else it would have to be wasted, simply because it can't be utilized at those times because there isn't sufficient storage capability for it. So if we were to assume that we have storage capabilities, it would be possible for us to very easily increase that capacity from the about 40%, even assuming it's a 70% efficient process, that we're able to store energy, convert it to hydrogen, and then put it back on the grid. And we're only losing about 30% of that electricity, which is a little generous relative to how many losses might be incurred in that process, but not out of the realm of possibility of a very efficient system. So under that circumstance, we could theoretically increase our wind production capacity by about 220%. And by storing the overages that we can see here, we're able to completely satisfy our state's demand for wind power. However, that's assuming that we're in the situation where we have storage and where significant enough investments are made, one, in storage needs, so that we can effectively store any overages at scale, to then redistribute when we need it in case of a low peak, such as, the February cold snap that I'm sure everyone remembers well. And then also it's assuming that we have effective management that's efficiently allocating all of our production so that we're overproducing enough and we're putting it back onto the grid at times that we need it efficiently. Under that circumstance, just some Under that circumstance, here's some fun key statistics in terms of production. So, as you can see, corresponding wind generation, we're again about 37%. Under this storage circumstance, we would need about 14.8 million kilowatt hours of storage, corresponding to about 625,000 kilograms of hydrogen storage. Under this circumstance, again, that's assuming we have sufficient storage, which is a major problem because currently we're assuming that there is sufficient storage, which, as we've said, hasn't been invested in. We could, in theory, based on arguments, say, okay, we don't need to worry about storage. We'll just ensure that we over-design the grid so that we can meet those peaks and then we don't worry about it. However, the problem with that circumstance is that we need to start considering an extreme event occurring that will affect how much we're going to be able to produce. Again, such as the heat wave here at the end of this period in June, or that cold snap back in February. For generous sake, we will assume that the grid could theoretically take a drop to near negligible load for 30 minutes. No, we'll say an hour. We'll be extremely conservative. So in theory, the grid can have, at small scale with current storage capabilities, enough power that we're able to completely supplement up to an hour of missing production where we're not able to necessarily meet our peak demand. So over this time period, let's consider how many times we have a period where we drop below. So as you can see from this critical demand, our minimum, according to this, is that we drop to about 0.9% in early January, where we're producing negligible production relative to our demand. So under that very, very generous assumption that we'll have, that as long as we're having gaps where that production falls and they're shorter than an hour, it doesn't matter. We'll only consider whatever the lowest threshold is that we have production drop below that longer than that. even then, that only gets us from 0.9%, which would be meaning we'd have to oversize our grid by about 900 times, to 2%, which means we have to oversize the grid about 500 times to manage to keep up with production. So as you can see, fundamentally, it's simply not viable to plan to just over-design a grid to be able to account for variability, because it simply doesn't work that way. On the other hand, you have some arguments out there that, okay, we don't really need to worry about having this massive production capability. As long as we have, sufficient management, we can over-design slightly and then have limited storage using what we currently have in place, and we don't need to worry about investing in storage. The problem with that is there's no investment in management either currently. So you can't exclude investment in storage without exacerbating the problem with not investing in management, or vice versa. So in total, that really brings us to what our fundamental research gaps are. Firstly, from a technical perspective, we're missing this holistic approach in which major efforts have only been focused on production, making it economical compared to fossil fuels. Therefore, really what's missing is we need efforts to characterize storage sites to model transmission networks, because current research in that area is insufficient. Most projections simply assume that salt dome storage, which is currently used for CO2, is going to be sufficient to achieve that, which fundamentally overlooks the fact that, one, salt domes are geographically disparate. There's only a few small locations where they're located, primarily Texas and the Gulf Coast region, where you have salt dome storage. Secondly, the fact that those salt domes being in those locations, one, only have a limited capacity that fundamentally cannot satisfy enough for the entirety of the United States. And two, the fact that with them being geographically located like that, you run into the issue that now, if you want to, even if they had enough capacity, you'd be increasing the losses incurred purely off distribution by orders of magnitude in order for you to be able to get any reserve storage from, say, Texas all the way to Maine or Washington, where the amount of energy you'd have to put in it solely to have pipelines transmit energy is 2, 3, 4, 5 times the amount of energy you're actually transmitting, which fundamentally is so inefficient that it wouldn't work. Therefore, more geographically spread storage locations need to be investigated, because depending on a resource that can only be found in certain regions, fundamentally cannot satisfy demand at scale. Second, there's this consideration of implementation and stakeholder engagement. There needs to be a massive initiative to really engage not only within industry in terms of investment in hydrogen, but reaching out to consumers to get consumer buy-in for adoption. As we mentioned before with our fun example of the market for cars that are electric, it took years for those to truly get adopted in any regard by people and consumers, because there wasn't enough engagement and focus on how do we make this viable and reasonable so that consumers will want to adopt it. Solely putting out a discount or a subsidy like the government did in the early stages without having the supplementing infrastructure behind it of fueling stations, mechanics who could, work on these electrical engines when they break down, isn't enough for people to be willing to buy in and invest in that from a consumer side. Secondly, you have this challenge really of economic funding, in that hydrogen is going to require significant funding and staged implementation to be effectively incorporated into industry. Current funding is heavily coming from government grants, requests for proposals, and venture type sources, which really won't work, because that's really being treated kind of like a gopher hunt, in okay, this problem has popped up. Now let's throw some funding there so that we can, get rid of it. But if we really want to achieve hydrogen at scale, we need to start looking at this as a problem of, here is a long-term plan for how we want to go from a technically immature resource to something that is used ubiquitously or almost ubiquitously in industry, which again is highly reflected in the fact that we can look at this task force report where there is a singular page dedicated to the needs of hydrogen distribution networks and storage, and very little attention paid to management, with basically everything being broken down in terms of their timeline, if you can call it that, of here are short-term goals with no times associated for how long this should take or what stages at which we're funding or looking to have solved these problems, and then a nebulous long-term goal of what we want to achieve eventually. That fundamentally cannot work if you want to coordinate an effort to bring something as market changing and massive a transformation as hydrogen would have to be in the energy industry for it to be functional. Finally, we have this problem of systems management where hydrogen really needs to be considered as a network of services in producing it, storing it, distributing it, and then end users. And there's uncertainty in realizing this because there are multiple goals that we want to achieve for different stakeholders along that process. So there needs to be a system level analysis of how do we manage all the goals we want to achieve, the uncertainty within that system, and then the fact that we have different agents acting at different stages of that supply chain to truly consider how we're going to evaluate the entirety of the network operation. And furthermore, back to our challenges with economics, this has to be a staged process, not an instantaneous process. So there really needs to be a plan for how you step by step address that so that you're building up the network without it having to be non-functional stages. Dang it. I am really struggling here. So finally, this brings us to our recommendations. So firstly, technology and research into hydrogen is not new. This is decades old, dating back to the 70s and the oil crisis back then. However, it hasn't been implemented because there hasn't been a holistic evaluation. Techno-economics, solely considering how do we make this technologically feasible and how do we make it cheap enough to be comparable to alternatives that are currently being used, is simply not enough for there to be buy-in from stakeholders for it to actually propagate throughout the supply chain and for consumers to use it. A holistic evaluation requires not only assessing technology and economics, but social motivations, risk management and mitigation, and then of course, there has to be a transitional analysis of workforce training and gauging local community impacts. You have to find out where in a community you can develop these resources that won't adversely harm the community or won't sacrifice some communities for others. And then you have a major issue in that, again, this is a shift in the entire industry dynamic. Therefore, this will reduce jobs in some places, but it will create jobs elsewhere. So there needs to be a plan for how do you transition not only the industry, but the people in that industry for that shift. Finally, there's really this major gap that's missing in that with all the computing power we have out there, prediction and simulation modeling are critical components to assess not only those impacts and interests of stakeholders without deciding we'll just crack a few eggs by implementing it now and see what happens and then make whatever sacrifices in the process of progress. We can do that all through simulation without causing any sort of harm up front. And we can assess not only those interests, but how they're going to affect one another. Finally, this project did have 3 key results. Firstly, there was a presentation that was given to Williams Company on this need. This paper was accepted in IDTC's 2020 to conference and then presented back in August. And then this completed business canvas and guiding research proposal was created. That was bad. Questions?
Thank you, Jacob. Chandra, I invite you to say a few things to reinforce and expand on what Jacob has said.
Well, first of all, let me congratulate Jacob for giving a good talk and a thorough analysis of the issue facing us if we have to convert to hydrogen economy. Whether fossil fuel stays or not, that's besides the point. But any source of energy has to transition into something else, as we have seen over the last 200-300 years, right? We changed from wood, biomass to coal, then coal to oil and gas. And even in the oil and gas, we switched over to gas more, oil less. So there is a need to have a resource which is clean, driven by the climate change, and also abundant. The question is, how do we make it at a scale and at reasonable cost with safety? Safety is always an underlying issue over there. And as Jacob said, a lot of research has been done in the past and for many, many years on how to produce cheap hydrogen. But no one has really looked at the total cycle, which he pointed out very nicely. And as we move towards this hydrogen economy, we need to consider all those aspects. And on the technical side, I think two things which he mentioned are the storage and the transmission. Because when we talk anything about on a global scale, we have to talk about storage. Currently, if you go to a refinery or some companies, they have storage tanks of some very limited capacity just to meet the need of that local entity. But for hydrogen to become the fuel of the future or the energy source of the future, we do have to think about storing at a very large scale. And just like right now, we store all the natural gas in the subsurface, which comes handy during the winter months or peak demand. Similarly, hydrogen has to follow something similar to that model. And one of the things which have not been, and that's my area of interest, is geostorage. Salt is not very good for hydrogen for the reason stated by Jacob. And also one thing which he didn't mention, that's the costliest form of storage. The most economic form of storage and which is available worldwide would be depleted hydrocarbon fields in the subsurface. They are the cheapest and readily available all over the world, large geographical extent. So again, thank you, Jacob, for bringing all this thing together.
Thank you, Chandra. Now the mics are open for comments, questions, so that we can continue the conversation. So just feel free to speak. Welcome.
Probably I had two questions in that sense, because I'm not very familiar with the field, but I just had. So are there studies for like evaluation of how much energy is spent to receive certain energy, right? So let's say if it is coal, then you use digging machines, then you use a conveyor belt to take coal from the mine, or you take trucks full of coal to the plant, and then it is transported, right? So from point A to the point of usage to the customer, like, is that a consideration as well? So how much we spend and then how much energy is generated from it, that is basically, is that considered an efficiency issue as well?
Yes, it should be considered an efficiency issue, and that is kind of a major portion of the point that I'm making here, in
Right.
that we don't really think about that side of the efficiency issue, because for hydrogen, since you're producing it from a resource that's already been produced, you've already made energy using oil or natural gas or solar. So you're going from electricity and then you're converting it into hydrogen. But
Right.
so generally when people start thinking about efficiency for this side of it, the question, that's the only efficiency they're concerned about, is what's the efficiency of getting it into hydrogen, and then what's the efficiency on the back end of taking hydrogen when it's getting used there. But my exact point is what you're addressing there, in that between those two phases, you have an additional step of wherever you're storing your hydrogen, once you've converted it, you need to get it from there to your end use. So you have significant efficiency losses in that, which is one of the major problems with the current view of overlooking storage. So basically, the current view of storage is you have salt caverns, which, as Dr. Rai said, are the most expensive, and they're also, again, mostly in the Gulf areas where they're located. You also have tank storage, which there's a limited capacity in which you can really do with that one. Or you have pumped hydro, which, similar to salt caverns, you face the issue of there's only so many areas you can do that, because you need a massive reserve of water to do that. And if you start deciding you're going to use fresh water to do that somewhere that's not an ocean or the Great Lakes region, you then are now taking a massive amount of water out of the supply that, would normally be used for drinking, agriculture, all of these other purposes that you're now running into. I mean, the state of Oklahoma has been in a drought for the past 3 months. I mean, most regions simply can't afford to sacrifice megatons of water solely for storage purposes. So you need something more ubiquitous than salt caverns, more viable without draining resources than pumped hydro, and capable of a larger volume than you run into with your issues with tank storage. Because the other issue is, yes, all of those are challenges that you could overcome by where you're locating it, but then, just as you've mentioned, you run into a issue of now you're talking about transmission over regions. And most proposals in terms of hydrogen that do consider transmission are considering that you run into at most 20, 30%, 50% if you're transmitting over a long distance. But what's defined as a long distance is 100, 150 miles. So if you're considering you're hitting 30, 40% losses every 100 miles in what you're storing, then even if you assume that current capacity is exactly what we need for storage, you're now, to go from somewhere like Maine to Texas for salt domes, or from the or get energy from a pumped hydro on the coast to the Midwest, you're talking 500, 600, 700 miles. And you're now, in order to get that transmitting, you're putting in 3 times as much energy as you're actually able to transmit. So again, that's another reason that it's important that you're not solely considering it from a production, and you start considering this larger term, how do we implement this efficiently consideration.
Is there a thought about decentralized storage where the end consumer is responsible for the storage itself, so that the transmission losses that we are talking about can can be avoided? Or, I mean, I'm not really sure how the transmission infrastructure is for hydrogen. So is it expensive than natural gas pipeline or a crude oil pipeline that's easy to put in? Or like, how does decentralization work for this, for hydrogen
with
storage?
hydrogen pipelines, because it's a much smaller particle, it requires a much higher grade of steel. It's
Right.
still, there are still very much steel pipelines out there that you can use that are rated and can be used for both. So they're not in everywhere though. So certain pipelines in place would have to be retrofitted for that. So yes, to answer your first part of that question, decentralized storage is ideally the way that you should be looking to an extent.
Okay.
That you want a resource for storage that is ubiquitous enough that it could theoretically be decentralized, so that you're not supplying everything from a single location in a region, but at the same time, you can't decentralize it down to, okay, we'll have a tank at every single house, every single facility, or even by township, because then you run into the problem of how population density starts affecting your maps. Because you have major cities, I mean, Atlanta, 6 million, New York is what, 10, where fundamentally on-site decentralized, on-site being, you know, relative there. But decentralized storage, simply, you have too many people in one place to be able to go out of your way to build a facility there for it. So you could, you know, say have one 50 miles away outside the city, but that's the limit of really what you can do. So you want to decentralize, you want it to be ubiquitous enough that you can decentralize to an extent to minimize losses without being so dependent on it being decentralized that you can't keep things at scale for the demand.
Yeah, no, you're absolutely right though. Because I after asking the question, I realized that the economies of scale for decentralized is, it's going to hit that hard, like that margin.
It's a balance.
Thank you.
But on the other hand, think about hydrogen can be used in number of forms. Okay. Just like if we replace hydrogen for fossil fuel, we can use hydrogen for generation of electricity. And the infrastructure for that exists. And it is not locally, you know, it's not decentralized. You have power plants long distance away. And other point I want to bring, which escaped my mind, see the policy right now, the Biden administration, this is the first time anyone has come in the government setting some policy issues on use of energy. Their slogan is $1 for 1 kilogram of hydrogen in 1 decade. Okay. So all the R&D or the policies are now being focused on production of hydrogen at $1 1 kg. They are not thinking about all the other issues which Jacob brought forth. And I think that could ultimately lead to the failure, or can lead to the failure of hydrogen economy. Right now, they're simply focused on how we can produce the cheapest hydrogen. They're not even considering in terms of energy usage. Now, if they say 1 kilowatt of energy at some cent, or let's say 10 cents in next 10 decades, then all these issues of transportation, storage, losses will come into picture. Right.
Thank you, Javed.
Thank you so much.
And thank you, Jacob, for your great presentation. And we know that there are different pathways that can be used for producing hydrogen. I would like to have your opinion that which pathway is most appropriate and economically feasible in the state of Oklahoma for producing hydrogen.
This is a fun question because it comes back to the original purpose of the business canvas, in that as an evolving market, if we consider solely what resources are in place, where the interest is right now, then by far, that would probably be a steam methane reformer, which is basically the most ubiquitous way to do it. However, in theory, if people are willing to make necessary investments, you have the North Central wind power plant that is going online in the next couple years. That's going to be producing what 1.4 billion gigawatt hours of electricity annually. So, I mean, if you're willing to make sufficient investments in the technology, investments like that mean that it could be just as economical to do it by electrolysis using fuel cells. So that's why, again, the point is, at the point of development, you need to be assessing the whole market, because shifts in focus, shifts in the interest, what you're willing to look at will drastically affect how the market as a whole can shape out as the market's evolving. That's basically the fundamental premise. You've hit on the head of why this is a necessary way to view the problem.
Great, thank you.
Anybody else? Page one, Jake, Tilani, Anirban, Hugh Nelson, Louis. Janet? All right. Go ahead, Janet.
I just wanted to say that I appreciate the very thorough presentation that you gave, Jacob. It's really very nice. And it points to a flaw that occurs very often in engineering, that we just focus on doing something and think that all the surrounding environment will take care of itself.
Yeah.
So thank you.
So to close, on behalf of the graduate student community, it is my pleasure to thank you all, and in particular to thank Jacob for this lovely presentation. Jacob is a very special person. He was a HERE scholar with us, and as Janet mentioned, he worked 2.5 years with us, the last year with Chandra Rai and Deepak Devagowda, to turn out this piece of work. He worked on 3 projects, and his interest is in starting his own company. What he has shown out here is his ability to identify opportunities, because to start his own company, he has to be an entrepreneur. The first thing an entrepreneur has to do is to identify opportunities. The second thing the entrepreneur has to do is to come up with a business plan where he takes calculated risks. And what Jacob has shown us here is that he has the competence and the capability to identify opportunities and certainly put forward a value proposition that is anchored in taking calculated risks. So it is very clear that Jacob is well set to achieve his dream of starting his own company. And we hope in X number of years, he'll come back to us and say, aha, guess what? This is what started my, was foundational to my journey to start my own company and make the mega bucks. So with that, thank you all very much. I'll stop recording, and we will continue as in the past to talk to whoever wants to talk to us when the recording is stopped.